You know that feeling when you're working on something and you solve a small part of it, only to realize, wait a minute, I have to solve that exact same thing again over here. It's so frustrating. Well, today we're talking about a concept that's basically the ultimate fix for that. It's called dynamic programming, and it's all about working smarter, not harder, by making sure you never solve the same problem twice. In this quote from Jorge Santillana, it just hits the nail on the head. Those who cannot remember the past are condemned to repeat it. In the world of computers, that's not just some philosophical musing. It's a very real, very expensive problem. Repeating your work can literally grind a program to a halt. So you can think of dynamic programming as a brilliant way to give our programs a memory. All right, so let's jump right in with a classic example. It's something that looks super simple at first, but it's hiding this nasty little computational trap. We're talking about the Fibonacci sequence. You probably remember this one. The rule is dead simple. Each number is just the sum of the two that came before it. It's an ancient idea, actually. It even showed up in studies of Sanskrit poetry to analyze rhythmic patterns. So to get any Fibonacci number, f of n, all you need are the two right before it, f of n minus 1 and f of n minus 2. Sounds easy enough, right? Well, here's where the trap springs. If you try to code this the most obvious way, using what we call recursion, you hit a major snag. Think about it. To get Fibonacci of 5, you need to calculate Fibonacci of 4 and Fibonacci of 3. Okay, but to get Fibonacci of 4, you need to calculate Fibonacci of 3 and Fibonacci of 2. Whoa, wait a second. We're already calculating Fibonacci of 3 twice from scratch, and you can just imagine what happens as the numbers get bigger. This thing, it doesn't just grow, it explodes. Yeah, and that explosion has a name. We call it exponential time complexity, or O of 2 to the n. What that really means is for every single number you add to the sequence, the amount of work you have to do basically doubles. It's just shockingly bad. I mean, to put it into perspective for you, trying to calculate, say, the 100th Fibonacci number with this method would take longer than the current age of the universe. No joke. So, yeah, there has to be a better way. And, of course, there is. The solution is built on one of the most fundamental rules in all of programming, something we call the dry principle. Don't repeat yourself. It's that simple. If you've already figured something out, just remember the answer. And this simple trick has a really cool, kind of weird name, memoization. That's right, memoization, with an M in the middle. Think of it like making a cheat sheet for yourself as you go. The very first time you have to calculate, say, Fibonacci of 3, you do the work and then you just jot down the answer. The next time your program needs it, it doesn't do all the work again. Nope, it just looks at the cheat sheet. And this right here just shows you the night and day difference. On the left, you've got that chaotic, branching RAS of the first approach, all those redundant calls. But look at the right. With memoization, the whole thing becomes this beautiful, simple, straight line. We figure out each Fibonacci number exactly once, store it, and move on. No wasted effort. And the impact? It's just staggering. By adding this one simple idea, just remembering our results, we tame this exponential beast and turn it into a simple linear problem. The work now grows at a nice, steady, predictable rate instead of an explosive one. We go from O of 2 to the n all the way down to O of n. That's not just a little improvement. That is a total, absolute game changer. So this whole strategy, breaking a problem into smaller pieces and remembering the answers to those pieces, it's not just some clever little hack for one specific problem. It's actually the core idea behind a huge concept in computer science. And now we can finally put the official name on it, dynamic programming. It's a whole approach for solving problems that have two specific characteristics. First, they have overlapping subproblems. That's our Fibonacci of 3 being needed over and over again. And second, they have optimal substructure, which is just a fancy way of saying you can build the best possible answer to the big problem by using the best possible answers to the smaller problems. Now, dynamic programming, or DP, usually comes in two flavors. The first is what we just did. It's called top-down with memoization. You start with a big question, like what's Fibonacci of 5, and you work your way down, saving the answers as you find them. The other way is called bottom-up, or tabulation. This is more like building with Legos. You start with the tiniest, simplest pieces, Fibonacci of 0 and 1, and you use them to build the next piece, then the next, all the way up until you've built your final answer. And here's a fun little piece of trivia about the name. Why dynamic programming? It sounds kind of complicated, right? Well, it turns out it was basically just clever marketing.
The guy who developed it, Richard Bellman, was working on military-funded projects back in the 50s, and his boss apparently hated the word research. He thought it sounded too academic. So Bellman came up with dynamic programming because dynamic sounded impressive and energetic, and programming at the time meant planning or scheduling. So it made his math research sound like some kind of practical, can't-object-to-it military planning.
Okay, so that's the basic idea with a simple number sequence. Let's level up and apply this to a much more complex, real-world problem. Let's forget about numbers for a second and talk about text. So imagine you've got two different sentences, or strings of letters. The longest common subsequence problem is about finding the longest possible sequence of characters that shows up in both strings. And here's the key part. The characters have to be in the same left to right order, but they do not have to be right next to each other. Let's look at a concrete example to make this super clear. We've got two strings here. The longest sequence of characters that you can find in both of them, in the right order, is ABAD. Notice how the lines connecting them show the matches. They maintain their order and none of them cross. Okay, but why should you care about this? Well, it turns out this isn't just some abstract puzzle. This algorithm is everywhere. It's a huge deal in genomics for comparing DNA strands. If you're a developer, you use it every single time you run a diff command to see what's changed between two versions of a file. And the same core idea is used in things like spell checkers to figure out the distance between a typo and the word you probably meant.
So how would we solve a problem like this without going crazy? You guessed it, dynamic programming. Specifically, we'll use that bottom-up tabulation approach. We're going to build a grid, a table, and each little box in that grid is going to hold the answer to a smaller version of the problem. Like, what's the longest common subsequence between the first few letters of string 1 and the first few letters of string 2? We're going to fill this thing in one cell at a time. And here it is, the completed table. The logic for filling it is actually pretty simple. When the letters for a row and column match, you look at the number diagonally up and to the left, and you add 1. If they don't match, you just take the bigger of the two numbers from either directly above you or directly to your left. That's it. By just repeating that simple rule and building on the answers we've already found, we fill out the whole grid. And where's our answer? It's sitting right there in the bottom right corner, the number 4. This elegant little table just turned a potential nightmare of a search into a clean, efficient process. Okay, so we've looked at two totally different problems, one with numbers, one with text, and solved them using the exact same core strategy. Let's boil this whole thing down into a simple recipe, a kind of mental checklist you can use when you run into problems like this. Step 1, look for those overlapping subproblems. Can you break your big problem down into smaller pieces that you'll need to solve over and over again? Step 2, find the recurrence. That's the rule, the formula that connects the bigger problem to the smaller ones. And step 3, solve and store. Start with the tiniest subproblems, figure out their answers, write them down, and use them to build your way up to the final solution. That's the recipe. At the end of the day, dynamic programming is more than just a specific algorithm. It's really a way of thinking. It's about looking at a big, messy, complicated problem and finding the hidden, simpler structure inside it. It's about exploiting that structure to get these huge wins in efficiency. So I'll leave you with this question. What other big challenges, not just in code, but maybe anywhere, are really just a bunch of smaller, repeated problems, just waiting for you to solve them once and remember the answer for good?